Good morning. I'm starting class with an empty class because the one person that always arrives on time is not here today. She's on business travel. But I want to get started. People, as you walk in, you will see me lecturing to an empty classroom, but there's lots of material that we're going to take care of today and the next week. We have 2 more chapters that we're going to finish off between now and next week, so we're going to handle chapter 6 today, and then we're going to handle chapter 7 next week and prepare for the final exam. In addition to that, we also have the take-home exam for me to go over. I have not graded it yet because I've been working on an alternative new project, final project, a much simpler project than what you do in project number 1. I've given you all through today to have work on project 1. I know it's tedious, time-consuming, but there's fun things you get to do in it, so I'm hopeful that I'll get some additional comments on that before the due date, which is later today. And then there's project 2, of which I have an old version posted on adaptive filters, which might suit the fancy of all of you. And then the new project, which I'm going to talk a little bit about if I can pull it off and finish pulling it together yet today, on filter banks and channelizers for software-defined radio front ends. It's a very interesting topic. It's motivated by a new component that I developed for the SIG-sys.py module, along with some other new components that haven't been pushed up there to GitHub. They're in the process with my co-developer. They're not actually up there now, but I've included a new version of the module should we go with this channelizer project. There's 2 assignments that are running right now, too. They're due next Friday, and then they're also due the Friday or the Monday of finals week. These are much simpler assignments. When I say much simpler, I mean much, much simpler. You're going to feel bored like you want to work on a second project, so I have that for you. We now have somebody in the classroom, which I'm thankful for. So it seems like a lot, but it's just staying busy and just getting value out of what you signed up for when you wanted to take this class. So with that introduction underway, I'm going to go into some of the details of the material before I actually start on chapter 6 on filter topologies. So I'm prepared to talk about exam 2, the solutions I've posted. I think because there's only one person in class, I'm not actually going to do that because I don't see a lot of value in it right now. Maybe we'll do that later in the class when we get more people here. I know we'll max out at 3. So we're up to 2 right now. Pretty cool. We might get 1 more and then we'll have 3 for the day since 1 is traveling right now. So what I want to do and what I had planned to do all through the weekend when I was working on this new final project idea, which I dumped mass amounts of time into it to make life easy, but to make life interesting and fun. I want to go through a little bit of where that's at and give you a taste of it. If you want to see what, as I say here, there's alternative project 2, which is an older project. I don't have the zip package up, but I think you would probably want to just look at the reader document and see what it's all about. It's adaptive filtering, which is an also very interesting topic. It's probably been, I don't know, it's one of the very first lengthy, well, not lengthy, but interesting projects that I developed for this class. So it's been hanging out in my portfolio for forever. I'm just going to give you a quick look at what an adaptive filter looks like, and this is the sort of the basic form of it is that you want to adjust the coefficients in this filter known as a Wiener filter. Why is it called a Wiener filter? The guy's name is Norbert Wiener, who developed Wiener filtering as a type of optimal filtering that would minimize the mean squared error. So minimum mean squared error is what MMSE is, and in its most generic form right here, we're trying to take an observation Y and compare it to a signal X by forming the difference at the output of the filter, and we're trying to adapt that filter so its coefficients optimally estimate X, in other words, and then minimize this sequence, and then the output will be the estimate of X. Now this is just sort of a textbook academic version of what the filter looks like. It doesn't actually come into play in operational senses that way. It has different versions of it, and the version that you study in this project is called an adaptive line enhancer. And an adaptive line enhancer just simply says if we have a signal that we can observe that has a narrowband component and a broadband component, and when I say narrowband, I think one or more sinusoids that have been corrupted with noise, and the noise is the broadband, the white noise, or nearly white noise. And what you do is you decorrelate the input signal in itself by putting in delay. In the case of white noise, just a one sample delay, and then this filter is going to try to estimate the minimum mean squared error estimate of the narrowband component, because it's not going to be able to know anything about the wideband component because it's decorrelated. So what will come out as an error is just the broadband component, and what comes out approximately down here is the narrowband, and that's the desired component. That says we have a signal in noise, a narrowband signal in noise. We're going to try to estimate it and remove a bunch of the noise. Does that, in a general sense, I mean, I think about everything I'm doing on my job this semester, which started about the same time classes started, and everything I do in here, and I keep thinking, at times I'll think, why does anybody care about this stuff? Oh, wait a minute, we're thinking signals and systems, right? So our context is we deal with signals all the time, and particularly waveforms is what I think about. In my job, I'll tell the team, I'm a waveforms person. I thrive on waveforms. Electrical engineers thrive on waveforms on and off throughout their courses and everything that they take. So trying to extract something from noise makes sense in a lot of contexts. It could be the broadband is something else, and I'm just going to sort of spin ahead to what this project has is probably one of the more interesting aspects of this basic adaptive filter structure, and you get to play with this in this project. It's called an adaptive interference canceller, and the adaptive interference canceller takes the same basic form as the adaptive line enhancer, but it has a little bit different context to it. This time, the wideband signal is not able to be correlated with itself because of the delay, and that comes out as the error signal. And in this case, a narrowband interference or jamming tone is what is something we're wanting to get rid of. So in this case, I give you an 8 kilosample per second recorded speech vector, much like the one in Project 1. It's one of those stock 8 kilosample per second speech files, and then you jam the system with an audible tone, and the adaptive filter does amazingly well. And in this particular project, after you just rework your problem number 1 to do this problem 3, you rework it, and then you get to listen to it, and then I ask you to zip up recordings from the adaptive filter interference canceller running with, I think, 0 dB signal to noise ratio and minus 10 dB signal to noise ratio is what I have in here. Yeah, the last part is at minus 10, and you're thinking, wow, that's amazing. It is amazing. I mean, the interference is very powerful, very annoying because it's audible. It comes in, and this filter adapts very quickly depending upon the adaptation parameter, and then you have the speech back again. And if the tone were to move around, the filter would keep following it to make sure it's mitigated. And you can extend that concept of interference canceling to a lot of different contexts. I know there's another student in here, Grant, who was talking to me about I don't know if it's senior design project or something he's doing in the antennas class. And an antenna array can be thought of, in particular, a linear array where you have antenna elements all in a line spatially. That can be thought of as an FIR filter. It's not too big of a step to think that, you know, each tap in an FIR filter is getting our input signal at a different time offset. And in a linear array, it's a spatial offset, but space and time are interchangeable when it comes to array processing. So adaptive interference cancelers can be done in the spatial domain too, where you interference cancel an undesired signal. And 5G has that as part of the design of 5G. In other words, there's multiple antennas on the base station, and they can form a beam in the direction of a user. The user doesn't have an array on their side, unfortunately, because it's hard in a handset and a cell phone to have a number of antennas, even though the frequencies are high enough for the wavelengths to allow, say, quarter and half wavelength separation is still kind of impractical at 2 gigahertz or 900 megahertz. But the base station can have that, so the base station can form beam in the direction of you, and then another user on the network will have a beam formed at the base station, and they can at least get that advantage. And that's part of 5G, is to have that capability of beam forming. But your imagination can run wild on this. Maybe it doesn't, I don't know. Has anybody ever thought about adaptive antenna arrays? I'm sure it's in some movie. What do you think? I mean, I worked on a project once that was a 3-element array that was in the nose cone of a cruise missile, and this was during the Desert Storm era, and it was being looked at as something that would be deployed on a smart weapon that would be flying. And the two things that make a smart weapon smart, maybe you're in the Army, what makes a smart weapon smart?
I mean, ability to change course at some point.
Okay, to navigate, right?
Yeah.
To be autonomous. So what are the two types of navigational systems that are generally on? A smart weapon would be an inertial navigation system, which is knowing about its traveling over space and its alignment with coordinates and things that might be programmed into it on launch, like where's the target and where am I supposed to fly to. But then another aspect of that for navigation is GPS. So I was working on an antenna array that was part of the GPS side of it, so that if the enemy on the ground was trying to jam smart weapons with GPS, jam the GPS signals, the GPS receiver could still function and aid the inertial system to together form a very accurate ability to home on a target. Sound reasonable? It's pretty cool. I mean, do I like seeing people and things getting blown up? No, but sometimes, you know, everything is not always what you think it should be. We have to be defensive and so on and so forth. But other ideas in wireless, definitely there. So that's what this project revolves around. There's a bonus part of it, which is to do an IIR part of it, which is far more complicated to get working. But there's a sample notebook and there's a lot of code in it, and this being a project very much like project number 1, besides having two parts to it, well, you have part 1, part 2 is working with a square wave, part 1 is a sine wave, part 3 is the optional part using an IIR filter, which is much simpler, less complex, but more difficult to get it to its algorithm to converge. And then part 3, the adaptive interference canceller. But like other projects, this has got a whole collection of hints and ideas on how to program things. So this project is mostly about programming algorithms to do something, and an adaptive algorithm, which might have been a dream that you had at some time in your life. Probably not this semester. It probably would have been a nightmare, right, if you were to be thinking about it. But, you know, challenges are always there. Pretty much everything I work on in digital comms, there's something that's at least a feedback control system embedded in an algorithm, or something that has to adapt and track. So this is an example of that. I don't talk about it in this class except in this project, so it's an introduction to adaptive filter theory, and it has at its core a very popular algorithm by today's standards called the least mean square algorithm, or LMS, which shows up in machine learning too. I mean, and to me, as a statistical signal processing person, a lot of the modern things that people have said, we're going to do data science, we're going to do machine learning, and we're going to do things with neural networks and other things of that sort. We've been doing those in electrical engineering in my domain for a long, long time. This other community that has come in and joined the bandwagon has really just put some new names on things, repackaged things, and then, yeah, AI is a big thing. But I had students work with fuzzy logic a long time ago too. I mean, things, as you get older and older, you realize technologies and ideas that people propose tend to come, and then ones that aren't working well will fade away, but then years later, they come back again. My professor advisor, Roger Zemer, said that I would see that, and I certainly have seen that. Neural networks had its first big surge quite a long time ago, and then it went away. Roger Zemer, who I respect a lot, when it first came around, and he was the department chair here, he talked about, we had one faculty member, Dr. Wong, he's now retired too, but he called people that did neural networks neural nuts, as if they've got crazy ideas. I mean, trying to model the brain, it's a simplification of what our brains can do, but it's still, I've had various students use things with neural networks in their projects. The most recent PhD student I had, who's from Kuwait, used it for hearing modeling, head-related transfer function modeling, so it's there. Okay, so I'm fine with this one, but I wanted to push on something different, and I wanted to push on something that I thought I could make more connected with hardware. But I kept tossing and turning. As I dumped so much time in this other project, I said, I at least have to put this out here as a backup and as an alternative, because someone of you, want to start on it ASAP. You don't want to wait for me to even another 24 hours to polish up what I've got, or you just plain, this sounds more interesting to you. So what is the other project about? The other project is a channelizer for use in software-defined radio applications. And I'm going to minimize that, and I'm going to drop down to the block diagram, which is not complete at this time, but if it will go down there. There we go. So I picked as a signal that we would channelize AM radio. Not very exciting. Do any of you ever listen to AM radio?
Yeah, we had one when I was very young.
Okay. They've been around for over 100 years. Yeah. They preceded FM radio. Believe it or not, the big people on the East Coast that invented AM radio, and then Armstrong, who perfected other receiving systems in radios, the super heterodyne principle is one of the things he's credited with. He introduced FM radio, and he died in a really sad state of affairs some of the big names in AM radio on the East Coast basically beat up on him, saying FM was just a bad idea. We have AM, we've spent all this money, and they pretty much destroyed his career, and he died, I don't know, moneyless, but he died in a really bad way. It's an interesting story, though. Why do I know about it? When I used to teach a class for non-majors called electronic projects, which focused on communications theory, the students had to write papers for me, and they chose Armstrong frequently, and I learned more about Armstrong just by reading their papers. But can anybody else think of an example where people that were engineering technology types that ended up being bashed around by their own peers?
Tesla.
Oh, yeah, Tesla comes to mind right here in Colorado Springs. Maybe Musk is thought of some people by being kind of crazy. I mean, I'm understanding that a little bit more because I talked to somebody in computer science after class 2 weeks ago, and I told him I was working for Blue Origin, and he said, you're either on one side or the other. You're either on the X side or you're on the, you know, some other space technology company. And I didn't really think of it that way, but he was thinking probably of his fellow faculty in computer science or maybe of the students. I don't know. I just think of them as both being after similar things. At any rate, I chose this for the channelizer application because it seems to fit pretty well. AM broadcast band is at a very low frequency, 470 kilohertz to 1670 kilohertz. And you think about what that means in terms of computers, microcontrollers, and so on, and you think, that's like DC. I mean, 470 kilohertz is not a very high carrier frequency, and 1.67 megahertz. I mean, when the first PCs came out, I think their clock frequencies, I'm thinking, were 5 megahertz or 10 megahertz. That was like the IBM PC when it first came out. But it quickly just kept, you know, moving up, and where we're at today is like way, way above. So this frequency band, though, has got a lot of advantages. It was simplicity. Everybody could own a radio, and everybody could have a radio that could receive stations from all over the world, actually, but all over the country in the evening, and then local stations in the daytime. But what you would what you would do with this radio, with a software-defined radio on its front end, is you could expand this out to a concept with a channelizer, and the channelizer idea goes well beyond what any radio idea from over 100 years ago was trying to do. I mean, you just wanted to tune into a radio station and listen to one program. The channelizer allows you to take your SDR and capture the whole AM broadcast bandwidth, and that's what this project does. I've used some hardware to do the capture, and then by channelizing, you can break it down. You can't do it all at once with the approach I've taken, but you can do it in stages. So you first channelize to 5 subbands, and then decimate by 5. And then each of the 5 subbands goes into another channelizer and breaks it down into 24 bands each, and then decimate by 30. And in this case, what happens is when you come out decimated by 5 and by 30, and you're sampling at 1200 kilohertz, which captures that RF band, you're coming out at 8 kilosamples per second, and it's speech that very understandable. So the logical question, and I want to see if you're thinking like I'm thinking, what's on your mind when I talk about a channelizer for a band of potential radio stations? Why would I care to be simultaneously tuning into all of those stations? This is unclassified, by the way. And I know there's classified applications, but if you can simultaneously get all of those streams going, what does that allow you to do that you can't do with just tuning in one at a time?
You can provide multiple output at the same time.
Yeah. Suppose you were interested in when stories break.
Right. Oh, yeah.
I mean, any intelligence gathering thing would say we can have the waterfront covered. If we're trying to move around and listen to a little bit of this and then move around to another station or whatever, we might miss something, and it's gone in space forever. We'll never see it again. But if we do this channelizer idea, we're just being megamaniacs trying to get all this information into our system. And I don't really have a specific application. My mind just wanders on what a classified application could be. We want to just observe any and everything that's out there and have our computer processing maybe sift through. In the case of analog modulation, it might just be doing some speech recognition or something and just seeing what is being talked about. But the rest of it I can't go into. I mean, I just don't even know the answer to it. All I know is it shows up, and where I'm working right now, they have a channelizer. I don't know what they use it for, but they have one in their toolbox of stuff. So this channelizer, though, was developed in Python, and when I made it, when I added it to the package, which as of yet hasn't been posted, but it's just something to play with. So in order to do this in my home, I got out my hardware that I have. So I have an RTL SDR, which is used in the comm lab. I have one of those. That's the upper box there. And then because it doesn't start receiving until you get up to about 50 megahertz or so, it can't capture these really low frequencies. RF front ends and SDRs don't necessarily cover from DC up to 6 gigahertz. They have to do it with different RF processing. So I had bought one of these many years ago as a demo object to hand around. How would you build an up converter? So this up converts signals from a lowly 100 kilohertz, which, you know, I'm trying to exaggerate a little bit. If we could squeal at around 10 kilohertz, you know, or we can hear up to about 15 kilohertz. That's only 10 times more, but that's called low frequency RF, and that's used. Even lower frequencies than that are used. Trying to think, what is the project that talks to submarines that are around the globe? When I was in school up at Michigan Tech, it was called Sanguine Seafarer, and they built a grid in the forest of upper Michigan so they could talk to submarines. A grid of antennas at very low frequency. And I can't think of the name of what it's called today, but it allows the submarine to not have to surface if it wants to get a command. And the command at those low frequencies is not something that's, how are you doing today? What are you doing? The command is much simpler than that. Are we going to do something with our nuclear weapons capability or not? It's part of what we do, what we have for defensive operations. But if a submarine doesn't have to surface, it can be very helpful to have that. So the low frequencies are good for that. Loran-C was a navigation system over water that I think is still functioning. It was in the kilohertz. I think it was under 100 kilohertz. At any rate, this up converts. So what it does is just pushes everything up by 125 megahertz. So it has a bandpass filter in it that can then go through a mixer and then take that whole band and move it up in frequency. And then the SDR can capture it. And on my Windows laptop, I was running Windows Subsystem for Linux on my Windows 11 laptop, so I could run the GNU Radio app, which is a software radio block diagram tool that uses Python and then orchestrates C++ libraries and compiles your code to go run a block diagram. And the block diagram then does what it's supposed to do. In this case, I used an interface called SOAPy, which is a open source interface for different types of SDR radios, and I can't remember what SOAPy stands for. It's software something or another, open standard in Python, and talks to the radio. I didn't have the option of picking my sampling rate of 10 or 1,200 kilosamples per second. So I picked the closest one the radio would support, and I set the center frequency to 126.07, and that then sets it so that the zero frequency that the radio is seeing is the 1270 kilohertz, which is right at the center of the AM broadcast band. And then I capture it into a binary file and then import that into Python and have a data set. It also runs a real-time spectrum analyzer while it's capturing, so you can see what's going on. So that I've done, and I don't know exactly how I want to use it all, but I have over 200 megahertz of data. It doesn't take very long to capture that amount of data, but we have that. So what's interesting about this is that the way you can work with the channelizer is it's a technology that is based upon something we're going to talk about next week, and that would be over here. It's based on this idea, transform domain linear filtering. It's one of the applications, one of the really nice applications of using a fast Fourier transform. So it's based on this concept called overlap and save filtering, which is actually in the SIG-SYS module. It's a very obscure function that I wrote way back when I wrote the book. It's called OS and OA is what they're called. Overlap and save and overlap and add is the other technique. But the idea is you bring in your signal as piecewise samples, and we'll be talking maybe more about this next week, but you bring in two endpoints and you work with a length FFT that's twice, that's two endpoints long, and then you bring in an impulse response that only is filling endpoints of the FFT. The notation in the function block here is a little bit different than it is in these notes, and then it's padded with zeros, and then you convert that to the frequency domain and multiply it times the two endpoints that you bring in at a time, and then you inverse transform that, and with overlap and save you have some circular aliasing that goes on, so you can only harvest n good points out of this, and you have to then move in another two n points, but you're only advancing by n points. So it looks somewhat wasteful, but it just has to do with the fact that when you convolve two signals together like a triangle or a rectangle with a rectangle, what happens? You get a triangle that's base width is twice the width of the rectangle. So you move along in segments like this, and all the filtering is done using transforms rather than doing the convolution sum. And the FFT can be very efficient at doing this because FFT engines can be in FPGAs, they can be in ASICs, and so on. So the added twist to this, though, that I have in this Python function is that if instead of on the fly taking the impulse response, I take the impulse response, load it in, take its FFT, zero padded like this, and then I have it stored away. And then because of properties of the FFT, if I take these two endpoints and I simply view them on a circle and rotate them clockwise or counterclockwise, this filter now is not just, say, a low-pass filter, it could be a bandpass filter. That was part of the homework problem that you worked on. Remember the one where you had different operations on impulse responses? You could make the filter something else. In this case, I can take one filter that's a low pass like this, and then by shifting it, it'll be shifted up in frequency or shifted down in frequency. So I can get many different filters, low pass filter, and then many different band pass filters without having to redo that. I just have to run it through the multiply operation in here and then stream out the signal filtered with a different center frequency. And that's the thrust of the approach here. So back over to the notebook. So that's what the idea of the channelizer or filter bank is. I can set center frequencies at the band centers there. If we move forward on this project, or some of you decide to pick it, I can change the step size in the algorithm inside so that I can effectively put up bandpass filters at different center frequencies and spacings, and then design the filter to begin with to, there's a typo in here I can see with my LaTeX code, but I can also redesign the filter. And at all times, one of the requirements, though, is when you're designing the FIR filter for this application, NFFT2, which is half the FFT length, has to be greater than the number of FIR taps. So this is an interactive thing, and the reason why I thought this would be interesting is it forces you to say, I changed my filter design, maybe the FFT has to change to keep this thing working. So the function now is pretty simple to operate. I design a low-pass filter. In this case, it's an equal ripple filter, and I'm sampling, in this case, at 1,000 hertz, and that's my sampling rate in my design function, and I want my low pass to cut off at 80 hertz, and its stop band to start at 110. I want the passband ripple to be 0.1 dB and the stop band attenuation to be 70 dB. So I designed that filter, and I don't remember what the length of that filter is, but I guess I should tell you what it is, though. So I'm going to do that. So it's 98 taps. 98 taps in the filter. So my FFT, I want it to be a power of 2, and we'll learn more about that next week. But power of 2, this has to be half the length of the FFT. So if I think about 98, that's just inside of 128, which would be a 120, half of my transform length. So I'm going to have to settle on having an FFT size of at least 256. And in this case, I said, I'll just go greater. I'll make FFT half length be 512 rather than 128. So I'll increase it by a factor of 4, but that gives me more control over the center frequencies because that enters into this equation right here. I can more finely tune the center frequency. So in the design of this, I will make the stepping, rather than clicking one stop and as I roll around my FFT filter coefficients in the frequency domain, I can have finer resolution. So in this case, I want to be able to step each band center by 180 hertz. So I go through this equation with my FFT length and the sampling rate, and it says I'm going to step in the nearest integer by 184 points. So that's what I do down here, and I feed noise into the input of the filter bank, and then as this runs, you can see what it's doing is I'm looking at all the channels with a spectrum analyzer to just see what does the power spectrum look like. And sure enough, I have a bank of 5 filters. Make sense? And if I tweak the filter design slightly, or tweak the center frequency, suppose I make that be only 100, then all the filters are kind of overlapping each other. And as a channelizer, this is not the functionality I'm looking for. I could narrow up each filter and then make the number of filters greater according to the way the function works. And then I could have narrower capture bandwidth. But to make the filter bandwidth narrower also increases the number of taps required. Anybody that's familiar with analog filter design knows that if you try to design a filter that has a narrow bandwidth relative to its center frequency, it takes higher Q components, or it takes a higher order filter to do that. A digital filter, same thing, more complexity, because it's just trying to form a narrow band out of a wide band, namely relative to the sampling rate. So in the case of the topology for this project, that's why I have a cascade of 2 channelizers, one to take it down to 5, and then take it down by a factor of 30. So it goes down sampling rate of 5, and then a sampling rate downsampling by 30, and getting tighter bands. And even at that, the filter bandwidths the filter orders become quite large. Set this back to 184. So in this project, I haven't fully decided, but I've pretty much decided that I'm going to give you the filter designs that work for the project, but maybe ask you to just explore some of the trade-offs that are involved here. Let's consider a simple trade-off. Let's suppose if I haul this out of here and just put it up above here, and this part of the notebook hasn't been published yet. This notebook hasn't been published yet either. But one of the things I like to be able to do is just see what the filter order is doing as I change the design parameters. So 98, suppose I want to make this tighter. Suppose I want to go down to 40 and move this down to, say, 50. See what happened? The order jumped dramatically. It went up to 285 at that point, rather than 98. All I'm doing is trying to make a narrow bandwidth filter. It's about 40 hertz wide, and it goes into the stop band at 50. I'd really like to have that even tighter, closer to, I'd like to have 50 closer to 40, but that's going to drive the order up even more. But just to give you a flavor for how that works, suppose I just experiment a little bit here and I say what's going to happen. 355. Can I still have that in my system and use an FFT length of 1024? Well, 355 is less than 1/2 1024, so it still works, right? Are you following the logic? This is not super hard math. I just have to make the lengths match so that I can do that. So let's go ahead. Now that we've kind of proven that out, we've redesigned the filter. I'll just go into here, comment that line out so I don't rerun and design the filter. And the center frequency stayed the same, because I didn't change that, but now the filters are all narrower. So I built a channelizer that's got narrower bandwidth, and in theory then I could go back to my equation and I could move them closer together. So I could make this be, say, 90. Okay, so now they're tighter together, and then I can take another parameter that tells me how many slices I want to get, which is how many clicks I want to do the filter with steps of 90 indices each. So I've got 5 in there. 2 represents how many filters I have above 0, and then how many I'll have below 0. So I have a total of 2n plus 1. So I could add in, I could go up to 3, 4, and 5. So I'll put in 5 bands above and 5 bands below, which will make for 11 total bands.
Do you also have to change that NFFT2 variable to 1024?
No, because NFFT2 means half, right? I could have written the function a different way, but I wrote it that way so you could always be thinking, if I have 355 over here, I know I have to have this number be at power of 2 greater than that. Does that make sense? So let me just run that now and see what happens. I should have, oops, What did I do wrong? Number of slices, 10. I had this at 5. No, I wanted it to be at 5. Mess that up, I think. No. Let's go back to where I was. See that I didn't mess something up. Okay, so that's right. I'm going to step 90 clicks in my filter coefficient bank, so each one of those does that and that. This should do it. Oh, I know what's wrong. Down here, I need to increase this number. It went from 5. I need to make it 11. That's what I was doing wrong. I'm just not processing all the channels with my spectrum analyzer. This is, as an engineer, you think about designing a system. When you design a system for real signals, you have to put some test signals through to see what's going on. So I'm putting white noise through it, and I'm trying to see do all of my channels come out stacked together like this, and that's what I've done there. So that looks pretty good. I mean, that's not necessarily fitting the AM broadcasting requirement, but it just shows you how you can pick different ideas to make this work. So I want to get into the other part of the lecturing. I thought about using test vectors for speech and then putting them up as AM radio signals, but I got my hardware out over the weekend and decided to just do the real thing. So in the real system, this is going to be hard and fast. We're sampling at 1,200 kilosamples per second. We're going to decimate by 5, and we're going to then sample at 240 kilosamples in the second stage. Then finally, at the end of the second stage, we'll decimate by 8,000. And I want to tell you a little bit about something that's pretty cool here. Normally, if we wanted to get this band right here, say this yellow one, if we wanted to get it down here for processing so that we could decimate it, what did we learn about in that one example on bandpass sampling? You just undersample, right? And then you get aliases that move around. But the way that these bands have been structured, if I just directly undersample, if I have this band, the signals that are in this band are not anywhere else, they're only in this band. So if I just decimate this by the appropriate factor, which I guess is it 11? Yeah, it's 11 in this case. This band will translate automatically down to here, and there's nothing else there. The only thing that is that signals that are getting in the stop band will leak around down in here, and those will come down into the band, but it's very controllable with the band stop of the filter, or stop band of the filter. So it's a very simple operation to decimate. So here I have an example that I've already put together. I'm taking my capture file, which is saved out, like I said, as a 200 plus meg file, and I'm using Python's save Z function, which saves it as a compressed binary file with an extension of NPZ. Then you have to use a dictionary in Python to get access to that particular element. This was created by me, so this has to be done this way to get it back. So there's how many samples I have at 1,200 kilosamples per second. And when I take a look at the spectrum of that, I see this. And I've shifted the frequency axis. Nominally, this would be 0 in the software-defined radio front end, but I've moved it so 0 now corresponds to 1270. Actually, 0 is somewhere in here, just so that this reflects physically the radio signal that I'm receiving. If that seems too magical to you, I just do that to it. Think about your car radio. How is your car radio working? It's an SDR-based receiver. You can display any numbers you want. You just know from the design what the real frequencies are that you're receiving. So in this case, I've done that. And I did this at about 10 p.m. 2 nights ago. What happens at 10 p.m. or after the sun goes down, AM radio has something that's been it's been a legacy with AM radio since the very beginning, I think. It's a concept called clear channel, and clear channel just says that because of the ionosphere, what do you learn in physics, or where do you learn about the ionosphere? I mean, in propagation, you learn about it in radio wave propagation, but yeah, astronomy. But the ionosphere, what does low frequency signals, the ions that are in the ionosphere form like a boundary. When you're trying to take a low frequency signal that has really large, long wavelength up to a bunch of ionized particles in there, what do the radio waves do? Do they penetrate and go through out into space, or they reflect off, right? Angle incidence, angle reflection, all that good stuff. So when the ionosphere comes in at night, because the sun is gone, now we've got the ability to have radio waves go up and hit something. When the ionosphere is higher, they will go up more straight up and then come down close nearby. But when the ionosphere is down, the rays can shoot up, and then they can go all the way across the country very easily. So this is what I'm getting at 10 p.m. with a long wire antenna. It's just a cacophony of signals that are out there. And I know you didn't grow up with the fascination of radio probably that I did, but I goofed around with radios because my father did amateur radio. So this has got signals from all over the country in it, plus some other interference. I don't think those are all active stations, but you can see how many dB down they are. So you can play around with this a lot, and I really don't know you don't have a lot of time, but it'll be interesting with AM broadcasting. The signals don't really jam each other so that you don't get anything understood. Instead, you're hearing one signal, and then you can hear another signal fainter in the background. Have you ever go out at night sometime, turn on your car radio, put it to AM, and just tune around, and you'll see that there's almost no really strong signal around. There's all these weaker signals that are noisier, but you'll be hearing other signals at the same time because they try to have, the radio stations have to abide by a rule that says if you're a clear channel station, you can stay on at full power at night, no problem. If you're not a clear channel station, you have to reduce your power at night so that you don't interfere with the other stations that have that right. And the ones that have that right are the legacy stations from way back in the beginning of radio. So AM stations in Colorado Springs, I think some might even go off, but they definitely reduce their power because they're not allowed. We don't have any clear channel stations in Colorado Springs. Denver has, I think, one. Maybe you know, I don't know. Have you ever listened to AM when you're driving across the country? The only time I would do it is if I'm listening to a baseball game or some sports thing. And the cool thing about AM radio is it goes, you can go all the way out to Kansas listening to it. And then, of course, at night when the skip comes in because the ionosphere dropping down, you can still listen to it. And you can think about stories. If you like talk radio, of course, you can listen to your favorite talk radio host because I think they simulcast from different transmitters around the country. So did any of you ever do that? Okay. Some of the stuff I captured that's in this vector, I listened to a little bit of it. I tuned in some stations, and there's things that you might find offensive that they're talking about because talk radio hosts are speculating on all kinds of things. They're mostly far right in their way of thinking. Does everybody understand that? Okay, so if we do this, or if you do pick this up, just understand I didn't create any of this. It's just what's there. It's what's approved. The FCC doesn't ban the language. There's no profanity because that's a no-no on the FCC, but they can speculate on all these bad things that's happening. It's no different than what the political campaigns were doing anyway, right? Same kind of stuff. So I could zoom in on that. So in Colorado Springs market, these are our stations. We have KVOR at 740, KRDO at 1240, KCSF at 1300, typo there. And then other ones listed, I just looked up the directory for Colorado Springs AM broadcast stations, and these are the ones that I found. These top three are the ones that are easiest to get. This one, however, when I first did this test, it was daytime, and I could get this one strong. At nighttime, it was pretty much gone, and I think it's because it's on a channel assignment that is it's required to turn its power way down at night. Does anybody find this stuff interesting? It's our history, right? And it's what we do to abide by, but during military or times of war, I mean, anything can happen. You can jam, you can blast people out of the water with RF energy to keep them from communicating, but I don't know. I grew up because my father taught. I have two other brothers and a sister. My sister's much younger. She doesn't really have any interest in this at all. She's a medical doctor, but all three of us took an interest in electronics growing up because our father did amateur radio. That's my test.
Spectrum that you took at 10 o'clock at night, you took that during the day, you get much less noisy.
Oh, yeah. It's almost nothing. Yeah. It's like barren. There was hardly anything there. And
clear tones at each frequency.
Yeah. Well, if you zoom in on it. So let's just take an example. That's what I was going to do next. Most of these are nothing that you will hear anything on, but let's just take right now I'm got this particular block set up to say FCC assignment of 1300, and then I'll on-comment this guy here, and then I'll run this again, and now it's going to zoom in for me. It's processing the whole big fat signal, and I'm running the video recorder, so it's taking longer.
So you're taking a live sample right now?
No, it's taking that test vector, which is stored. This is routine for guys like us, guys and gals that work in industry. You get test vectors. If you're a systems modeler, you get your test vectors from the FPGA developers or anywhere, and then you work with these capture vectors. So there it is, zoomed in, and the axis is plus and minus 10 kilohertz right now. So this is at 1300, and this is talk radio right here. The carrier is very strong in AM broadcasting, very inefficient, but it makes the reception very simple. This, again, is the 100-plus-year legacy of AM radio when it was invented. The rest of this, there's really very little other content. There's interference in here that you'll be able to hear, but that's just the noise that's down that low. So I do a capture here using the same filters, but I'm not doing it with the channelizer. I'm just going to take the signal right at, I'm going to low-pass filter it. See, I might be missing something. Never mind. That's where I designed the filters. And those will be the filters that I know work with the channelizer as well. And then what I do here is, rather than using the channelizer, I'm going to use complex frequency translation relative to the 1070 center frequency of the capture and move a signal, in this case 1300, down, and then move it down as a complex spectrum. So the spectrum is all the way across. When I do that translation, I just walk it over. So now the signal of interest is at 0. The channelizer would take care of that automatically, but now we're going to do that. And then I decimate in here. I filter it once, decimate by 5, and that's, plus and minus 120 kilohertz at this point. That's way too many signals can land inside that band. So I do it a second time. It's already centered on 0, so I just have to filter it a second time with a second filter to narrow it way up, and then you see the 30 up there, that's decimating it by 30 again. So now it's down to just 8 kilohertz. And if I look at that spectrum by 5 and by 30, then there it is, kind of zoomed way in right now, and that's now at 8 kilosamples per second, so AM radio you can detect very easily. It's something called an envelope detector. Whether it's analog or DSP code, the envelope detector in DSP is just taking the absolute value of that signal, and now it will have a bias on it because of AM radio biasing with that huge carrier. So then you have a second operation to remove the DC. It's a DC block. If it was in the lab with electronics, you would have an envelope detector as a single diode, and then you would have a coupling capacitor to block the DC. You've been there before? I mean, the comm lab, I have you do that, but simple, and you don't have to have an SDR to do AM radio. You can do it with almost nothing, a diode and an antenna and a capacitor, and you can actually hear AM stations strong enough. You know, this building, not so well because it's got a metal studs in it. Your home has wood studs, so our high-frequency signals pass through your home easily. Here, we're in a giant screen effectively because of the construction of commercial buildings with metal. You have to get close to the windows and actually get it, because think of all the grids around the windows and the walls like the grid in a microwave oven. It blocks because the wavelength is too big to get feed through.
Act like a Faraday cage.
Exactly. FM can get in easily, but AM has a much harder time because of the wavelength difference. Does that stuff make sense? These are really practical things that you have to kind of be around and kind of understand why.
Wavelength is smaller, so that's why the frequency is lower.
Low frequency has a big wavelength, and it hits that grid, and it's like, I can't get through this. It's like a solid screen, just like you said, a Faraday cage. And if it's smaller wavelength, then it can penetrate. That's why our cell phones work, and Wi-Fi and all that other stuff. Why did I studied RF, microwave, and comm systems, and then electronics is kind of your backbone, but that's kind of what my undergraduate degree was in, besides math and stuff too. So now that I have that down, I can take a listen to it. I can look at the waveform down here too, but let's just take a listen.
6, and then the Niners at 5 and 7. So the Niners at 5 and 7 have a chance to make the playoffs, where the Cowboys at 5 and 7 do not. I mean, they do, but they don't. Because the records, if you just look at the conference, if you look at the records in the NFC, it's Lions 11 and 1, Eagles 10 and 2, and then the third seed team is 7 and 5, the fourth seed team is 6 and 6, and then the fifth seed team is 10 and 2, and then 9 and 3.
Right, probably.
Yeah, I don't know if they're going to make the playoffs.
Okay, so that was on there. I could tune in another one, and it was talking about some pretty intense, right wing stuff. It was just very suggestive discussion. It's what I captured though. I could pick anything else. It takes a little while when my video is running to distill it down, and it will take time on your computer. But so I think I've spent quite a bit of time on this. I get excited about things. I'm pretty crazy about playing with stuff. So.
From a high level, like, is the idea of a channelizer that you can select a specific frequency and bring that down to baseband to process and listen to? Is that?
Yeah. Well, the idea, the channelizer just says I'm going to get all of them in parallel. I'll have everything, and I don't want to have all that playing in the background. So I thought, if I write this up, I would say pick your 2 favorite stations from this implementation and store them in the WAV file as the left and right. So when you ship that to me and I listen to it, I will hear station 1 by plugging one earbud in, and then I can hear station 2, and that will be your proof of saying I simultaneously had this captured, because the algorithm to demodulate it is really simple once you get it that far down. You will have to take it from one of these outputs. I just didn't complete my block diagram. It's on paper, but I didn't finish it yesterday. I was feeling guilty about not grading papers, and I've invested so much time in this. and I started this weeks ago. I mean, I started with this new component, and I said, maybe I could do something for a project. But these things take time. And you know that. Working your project, one, is taking some time probably, right? And necessary evil of working anything hard is that you can't do it in one sitting. Have you come to that conclusion? You have to work for a while, you get a little bit frustrated, and you walk away from it and say, what am I doing wrong? I just can't see it. You walk away, come back, eat something, go out with the dogs or whatever I do. I mean, then your brain clicks. It's like, because you can't take that out of your mind easily, right? It keeps sort of subliminally in your back of your head like, what's going on here? How come I can't make something obvious work? Have every one of you been there before? It's going to be your life. I mean, it is your life, right? You always are solving some sort of a problem. When I got married, my wife had a dog, and the dog was scratching up something in the house when we were both at work, and I had to go to the lumber yard and get different sheets of plywood and build barriers around areas that I didn't want the dog scratching on our brand new house. It didn't work. The dog found another thing to go try to do when we weren't at home. That was before video cameras. Now you'd probably get a video camera set up and see what's going on when you're not at home. If you've got animals, I mean, kind of a classical thing that goes on. But that's a problem, right? You still have to solve it somehow or another. It doesn't involve electronics maybe, but so that's a good question. Each of those down by 30s, and there's no need to have an additional filter before you decimate, because I taught you earlier in the semester that before you decimate you have to band limit, but this channelizer has already done that band limiting. It might not be taking it from DC, but when you downsample, it'll use that undersampling concept and fold it down, and nothing else can occupy that except what leaks through from the stop band attenuation. So it's not a perfect design, but it's a concept, and I don't really have a practical application. Like if a story was breaking and you were capturing the entire AM radio band and you were word spotting on all those streams, you would probably see a distribution of times of when this information came across the airwaves from the different sources. What would that mean? I don't know. I mean, again, my mind could wander, like for anything that could go on with radio signals. And intelligence gathering is thinking up ideas or has thought up ideas. I can't, if I knew, I couldn't talk about it, but I can only speculate on it. But these are things that you do though, right? If I could do this, how could I, just testing things sometimes requires you to think up ideas. So yeah, the single channel is what I did quickly, but this works as well. I have that in the notebook, and I will have parts of it in there. I just have to think about simple things to have you play with. And if you have ideas on what you'd like to investigate, I don't want to make it really hard mathematically. I just want to let you say, let me use this framework to try to study something, and then you can drill in. You can be a detective and drill into this spectrum over here, which I have to rerun it again because I zoomed in, but just pick something different, and the channelizer will give you that opportunity to see as many bands as you want. I'm not going to require you to build all 5 of the final channelizers because that gives you 120 channels. It will take a while for the computer to crunch through 120 channels with FFT processing. That I'm not going to ask you to do. I've got simulations running from my work on a server that they've given me access to that are running 3 hours per collection of stuff that I'm simulating. So I know that this can get out of hand, and save that for a graduate degree, like for you and your master's thesis project. You might end up doing something that takes some CPU time to do that. So it's almost time for the break. Any other questions or comments? The adaptive filter project, which I've already let you take a look at, I suggest reading through that, and then hopefully we'll have something to push up there on this one. I think what I'm going to go for, though, right out of the chute here, unless somebody throws an arm up and say, I don't care, I don't want to do that one, I'd rather do this one. I'll plan on letting you do one or the other, and then you can pick. And there's a bonus option in the adaptive filter project, but the most exciting part of that will probably be doing the adaptive interference canceling. It's very impressive, very, very impressive when you see that work. But you have to get an algorithm working, and that's probably the frustrating thing, but I give you a lot of hints on how to do that, and it relates to your adaptive antenna project because it's an FIR filter, which an FIR filter, like I said earlier before you got here, is like a linear array in antenna theory, just a bunch of elements that are spaced by half wavelength or quarter wavelength, whatever, along a line. And a spatial array is a two-dimensional FIR filter. You know, they're on a grid, let's say. And then the project I related to was the three-element Y array, which sat on the nose cone of a cruise missile, and then had to direct nulls in the direction of jammers. So that may be of more interest. This is just kind of more of a hobby thing. If you ever were interested in radio signals, and I had wires around the house trying to make a long enough antenna, and my wife ran into it, and she was like, what's this wire? It's over here. I said, well, I just unspooled a bunch of wire to make a long wire antenna. And yeah, nice trip cord. It's copper wire, very fine gauge. I didn't want to kill anybody in the house, but. And then it was 10 p.m. and I said, my signal that I was listening to is gone because it went to low power. But then I had this cacophony of, skip signals out there, and I thought maybe that's more interesting. So, okay.
So we do either this project or the project that's already on?
The one I talked about earlier, it's this one.
Okay.
Let's see. Adaptive Filters project. I don't have the zip package pushed up there for this one just yet. I've got it, though. It was called Final Project Zip years ago, and I used it. And I just have to put it back together again. I need to inspect the notebook to make sure it's good to go with the right stuff in it, the right header in it. So this one you can read on, and that I want you to read about it and see what you think about it, and then talk back to me. I have a lot of info on this, though, and it's all right in this document. And then the other one is what I've been going through, and I'm kind of giving you a flavor for what it will turn into. It will be less less programming involved with the radio project. I'm pretty much just going to give it to you, and I'm going to say, do something like vary this around and show me what happens. And then I'll have something like find 3 radio stations and combine left and right together or something like that. I haven't really decided, but you will send zip files to me of WAV files, just like in this project at the very end, I have you send a zip file for 2 different SNR levels with the interference canceller, and then waveforms in the earlier part. So similar type concept. I don't want to spend hours grading either, and I can listen to something and I can get an understanding, is it making sense? And you'll know it too when you zip it up and put it into Slack. You'll say, "This sounds good. I sent the right file," and it'll all make sense as the finale about how that's going to go. Meanwhile, we have this interesting topic today, and there's a little simulation problem at the end of this homework assignment, which is due a week from this Friday. And then the last one is due, like I said, at the start on Monday of finals week. So I guess we're going to take the break, but let's just quickly look at calendar-wise where we're at again. We're here. We'll do Chapter 7 on the FFT next week. The exam will be on the 18th, so the homework that goes with the chapter we're covering the rest of the period is due over on this Friday, and then the Chapter 7 problems that go with this lecture are due over here on Monday. And they get progressively less and less problems, more options for bonus points, and far trivial, more trivial type problems. You're gonna think about this this is so, the amount that you're grabbing onto is so minimal compared to what you had to go through. Assignment number 6, which I haven't graded yet because I may grade the exam first, because it is a killer. There's a lot of detail in there that you had to put together.
Question, doctor, will you be releasing the grade before the 20th, so I know if I should walk or not?
Oh, yeah. Yeah, I mean, I only have 4 of the final exams to grade. Okay, I guess you'll ask me for the rest of the story. The exam will be on the 18th, and I don't think it starts at 8 a.m. Make that an assignment while you're out on a break here. I think it probably starts at 10 or something weird like that. You already know what it does?
There should be a schedule.
Yeah, there's a schedule. You can tell me when we come back from break. So I give you until Thursday to get the final project in. A lot of people will probably turn it in even before the final. That's usually happens. And then if I'm supposed to have it all done by the 20th, generally the rules of the university give me through to Monday. But I will have an idea, and you'll probably have an idea. My intention of next week is I maybe won't go over exam 2, but I'll have compiled all the info, and I'll post that, the histograms and the current standing from the homework so far and from the exam so far. So you'll have a status on that. I just don't have that right now.
The final fully cumulative?
Yes, but more emphasis on the latter parts. And good question. Since we're focusing on that right now, I'll jump over to that. I'm going to repost this, but it is in here.
I think the final's at 8 to 10.
Okay, that's what it is.
Yep.
So we have this guy right here, and I'll push this again. This is from one that I could lay my hands on, fall 2018, but it'll be very similar. This takes you through the emphasis, and what I will do next week is I will walk through something like this, and I will mark on this and say, no worries about this, but yes, I'll have one of these, maybe one of these, maybe one of those, that type of thing. So I go through this whole thing. And then this down here just talks about the FFT stuff, which is the new material, and the topology stuff, which is the new material, which will be emphasized a little bit more, but it's maybe a third of the exam is the newest material. And this stuff will make sense next week. This is like a quick synopsis, and it's open book, open notes, so, this paper or any paper for that matter. And you can bring your book in, and if you don't have a paper book, I will have one of mine in here to pass around. If you want access to the notes that I wrote, what people have done before is they've agreed that they will have a copy that they made and bring it in and share that too. I don't want you to have to just burn lots of paper, so what do you think about that idea? Does somebody already make a paper copy? I used to have one in my office that some student had left me with, but I don't have one made right now.
A copy of what?
The course notes, because you can't access a computer during the exam. If somebody has done that, and we have one student out there, and she'll maybe respond after she watches the video, but I'm fine if we can have that. I just don't have it printed, but somebody has done it. And I used to have a copy in my office, but 2 years ago I recycled that somebody had made and left with me.
So can you explain, so we are doing project 2 and we are doing the final exam on the 18th and the 19th of the due date, right?
Yeah. Like I said, the final project, you'll probably find that that's a lot easier than what you might think, but you can read through the adaptive filter version, and people will. It's been amazing. Usually, people get things off their chest very readily at the end of the semester. They're like, we're having our shutdown early today. Almost forgot about this fun thing.
So what was that great option with the final project that you talked about initially on the?
That I optimize between the project and the final. So it's like a 25% versus 30. I think, actually, I put it, I reviewed it right in here. Option number 1 is it toggles between the final exam being worth 30% or 25%, and what that does is it changes the computer project between 20% and 15%. So I optimize that. If you do really good on the exam and the project not so good for for whatever reason, then it will weight the exam heavier, and it, vice versa.
Both are 45% of the class.
Yeah.
Okay.
Yeah. The projects are something you have control over, though, because you've been working on them, and you guys could work as a team.
I don't know what it is this time around. Did you already publish that document?
Publish what?
Project 2.
Project 2 is published only for the adaptive filter, but I have the rubric at the end for that, and I pointed out the rubric when people have asked. For Project 1, there's, at the end of that document, there's a rubric like this. This is how I grade it, so you know what parts are worth. I mean, I can only do so much, but I think I do a lot. I mean, because I want you to feel like, hey, we're being taken care of, even though we have to work hard.
No, I was saying, like, if we can decide on what we're going to do, because you have 2 possibilities for projects.
Yeah. If you don't like my wonkiness of not having it all tied down, I'm going to try to make it at least as easy, but probably easier than this, because you don't have to write an algorithm and get the algorithm working. The hardest part about this, but I have lots of hints up here, as to how to write the adaptive filter algorithm. Once you have it working, it'll work for the entire project. So I have a lot of discussion on it in here, in the hint section, about how to actually write the adaptive line enhancer and then switch it over to the adaptive interference canceller is very simple from what I already showed you, the block diagram. You just take the output from the different port in the algorithm. And the notebook has a lot of this structure in it. It just has a section in the middle of it, though, kind of like this, where I have no code in there, and that's what you have to write. It's not an extremely hard thing, and the paper walks you through what steps you have to code in that area. So it's pretty good. It's been a really well-liked project over the years. Students have told me they really liked a chance to play with adaptive filters. But the radio idea is intriguing to me, so if nobody wants to do it, I'm fine also. I'm sort of, when I came in today, I said maybe I should just quit. I've thought about quitting every day for the last 5 days. Like, let me just give up on this, because I've spent so much time. But the more time you spend, it's like I just feel now like I have to kind of polish it off to the point where it still can look like an option. But the adaptive filter project has been lean and mean for people to work and been satisfying. No one's ever complained about it not being satisfying, especially with the adaptive interference canceller. Maybe I'll demo that next week, just to let you see what it sounds like so you have an idea. If I know people are going that way when it works. If you adjust the coefficient and you turn the system on, you'll just hear a little blurb of tone, and then it'll be quenched down and you'll just hear the speaking. It's that fast at adapting. Okay, let's take a break, and I want to talk about topologies before we run out of time, because I only have today. So can we do 10 minutes? Be back at 20 till.
I don't see the adaptive filter project on your website.
I saw it.
Oh, yeah. I think it's the wrong one.
It's right here.
If you click on it, it shows like GPS something.
I don't even have that link. Maybe you need to refresh or something.
You might have to refresh.
Oh, there it is.
It should have this interesting surface plot in the middle of it, which talks about optimizing. So it worked before I left the house today. I did just post it this morning, though.
I see it now.
Yeah.
And you said you post the radio one later?
Yeah. Yeah. What should I put my priority on, grading papers or finishing the project? What's the deal? This thing's flaking out on me. Let me yeah, take your break, then I'm going to ask you a question about preliminarily what your interest might be, just so I know how motivated I should be to work on the radio one. But don't answer me right now. Wait till you come back. So I'll pause the recording for a bit here. Okay, we're back from the break, and we were just talking about which project seems to be more interesting. And of the 3 people in class right now, they're interested more in the channelizer, so I'm going to work on that when I get home. The adaptive filter project, though, is tried and true. It has been tested many a time. The GPS receiver was 2 years ago. That's a fun project, too. But I would say, overall time's sake, the adaptive filter has been used more and been tested, tried and true. But to let you know, not that you don't know already, I'm crazy enough to try another project because I'm just, as I do more work, I get more excited about new things. Okay, so we're going to switch over now and dash along to structures. And this is going to be kind of like going into the circuit theory side of digital signal processing. So we have representations, block diagrams, signal flow graph, and then we take that into the various structures for IIR systems. We have direct form, we have cascade and parallel, then we have transposed signal flow graphs, and all of these topics relate to topologies. It's like, how would you implement the filter, whether it be in FPGA or in code? You get to decide. The topologies are different. The end-to-end result is the same in an ideal setting, but if it's dynamic range, finite precision arithmetic, efficiency of code, layout in FPGA, layout in an ASIC, there's all, pros and cons to them. So that's the reason why this topic comes up. And then at the very end, we get into finite precision effects, and you do have a homework problem in set number 7 that deals with finite precision effects. And, in case I'm dashing so fast at the end that I don't get there, I did open up the PDF version in case I don't get a chance to run the notebook. This is the notebook for Chapter 6, which is posted right now. And the homework problem that you do is very similar to what I do at the end here. What I'm doing here is I'm just going to design a low-pass filter, very similar to what we were doing for the channelizer, Ramez low-pass filter. And then we'll come along and we'll quantize the coefficients with, say, 14 bits, set the dynamic range to plus and minus 1, and set whatever setting I say in the homework problem, and then you go and look, you'll study the impact of quantizing the coefficients away from double precision to, say, 14 bits or whatever, and then you get to just do plots like this. The ideal response will be the blue, but when you start quantizing coefficients, you generally see the stop band is getting the influence of the quantized coefficients.
I have one question, Doctor, before we proceed there. The project 1, do you want just the Jupyter notebook or the entire compressed file? Because that would be almost 15 megabytes.
No, I don't want the compressed file. I want a PDF that I can mark on. That's what I want. I want a PDF. So you have to render it out. You have to render it out somehow using one means or another that we talked about earlier in the semester.
Okay. Too easy.
Yeah. Is that too easy?
Well,
rendering it out for most people is like, this is a pain in the butt, but this is how you can communicate.
I've been doing that the entire semester.
Yeah. some people, what they'll do in this project is they'll give me two things. They'll give me the PDF, and then they'll have a zip that'll be a monstrosity, and I will take both of those, drag them into my folder in iCloud, which is where I store my stuff for grading, so it's backed up, and then I'll grade your project. I'll listen to, I don't guess you don't record any zip files for project 1. Give those to me. I don't think. You listen to things, but you don't save anything as a zip.
Yeah.
So you'll do that, and then that big zip will just sit there, and if I have to look at it, I'll, with great reluctance, open it up and see what happened. So I want your code listings in your PDF document, but I don't want to have to run any of your code. I want to just see it all there, and I want to have it follow the flow of the rubric. So it'll be nice and easy for me to find it.
The way we have it here, like parts by parts, is
Mhm.
it okay if we render it to a PDF? Or
Yeah,
use this-
yeah,
like,
yeah.
Because I could copy paste it in Visual Studio and just give you the entire code base.
Now, well, I want the code that's in the cells, like for all the experiments, and then answering all the questions. I don't want to be missing an area in the rubric where it says, I give you points for code, right? Just look at the rubric and you'll see that, I get 10 points to have code. I get 5 points for this analysis or answering this question. I get 2 points for that. So I definitely want
So
that.
something like this where we talk about it here with the markdown and then have slots.
Yeah,
And codes are right there, so this is good.
yeah,
Okay.
yeah. I will be looking, and just if you're not sure and you want to compare each other since you're working as a team, look at the rubric. And if you say, but this is not in this same area, it's like here I'm grading problem 2, and the code for it is way, way out of the way, and I'm confused, I'm going to get really frustrated. I want to see it all flow like the rubric shows it. All the stuff for 1, all the stuff for 2, and so on.
Too easy. And we have it exactly how you gave on the
Yeah.
health one.
Yeah, and I've been training you on that all semester, right? Your boss will want it differently.
Yeah.
I mean, I'm doing stuff, I deliver stuff to team members as PDFs. I give them notebooks, but most people, like the FPGA developer, implementer, he's happy with block diagrams and results from code. He doesn't want, he looks at the Python base, but not the notebook. It's a different philosophy than here, but very similar, just the same. So at any rate, this is the most interesting problem of problem set number 7, where you'll actually do some experiments and just make some observations about this. And this is very sensitive, and you will explore that, how if I just change the number of bits a small amount, these little bumps will drop down and it'll become just little changes. It won't cause, like here it was supposed to have equal ripple down to -70. It popped up to about -63 or so. It'll go down further. And that's quantization effects there. When I first started teaching, we didn't have it that way. So it's gotten much more interactive. And I had to go through a data science approach I'm taking to solve a particular analysis problem to the local team. So I was in the office with my laptop on the projector, and I was using VS Code and the Jupyter notebook in VS Code. And they wanted to see everything and asked me questions about it. So when we start trying to represent how we implement things using topologies, we start first with the block diagram idea. And the block diagram technique that's used is very simple. It just has a summer when signals sum together, and then if there's a gain along a path, it'll just be a wire that has a direction arrow on it, and then it has a coefficient next to it. Or in the case of a block that has a one sample delay, it's just a block with a z to the -1 in it to represent the one sample delay. This will very soon get streamlined into a signal flow graph, but this is the block diagram form. So big exciting thing here is that the book at this point The pen will start working. Yeah. That was a plus sign earlier in the course. In this chapter, it changes to a minus sign. Be very careful on this when you're working the homework problems. Be very, very careful, and I'll point these things out for the time that remains. It's just done for convenience, to make the block diagrams make more sense. So now when you rearrange the block diagram to look like the difference equation, where you have the output in terms of past and present values of the output, or past values of the output, and then past and present values of the input, you don't have a minus sign hanging around in there. That's all this is done. Earlier in the semester, there would have been a minus sign sitting right over here, and it's just, they just change it. So that means effectively that these coefficients have a sign change on them. Sorry, I'm not a fan of causing confusion at the end of the semester when your brain is whirling fast, but it is, you can hop on board. So the direct form implementation just takes these two sums on the right-hand side there and just directly implements them. So it starts off by saying we're going to do all the feed forwards by just having a tap delay line running down here and summing them up, and then going across this interstage point called V of n, and then summing up feedbacks coming up. And it seems silly, maybe, to say all those delays are in here and all the individual sums are in here. Why can't I just wire them together? But the point here is to try to show the resources that are being required. How many sums are required? How many delay registers are needed? And then the most expensive thing typically is how many of branches where you're having a coefficient multiply. And that would be like a 16-bit multiply, which would expand out to 32 bits, and then you would truncate it or round it back to 16 bits. Now I'll talk at the very end how you can change these topologies around so that you're less sensitive to coefficient quantization. But right now we're still thinking of ideal infinite precision math. We're not really into the aspects of coefficient quantization yet. So this is called direct form 1, and this is what some of the homework problems deal with. It'll just say implement something in direct form 1, and that's what the block diagram will look like, except you'll limit the number of coefficients, you put numbers on the coefficients, and so on, like that. So it's composed of the two substages, the feed forwards only, which is right here, and then the feedbacks, which is right here. So if we go to the Z domain with that, we can say we have an H1 transfer function for the feed forwards, an H2 system function for the feedback part. And because linearity allows the order to be changed, so rather than doing feed forward, feedback, we can go feedback, then feed forward as a cascade. And if we just simply rearrange the difference equations in the Z domain to show that, then we'll do the feedback difference equation first, the feed forward second, and from a topology standpoint, I zoomed it in because right here we're doing the feedbacks first, then the feed forward second. But when you look at this picture, I always visualize, and this is my strange analogies, right? It's two people sitting back to back. So their backbone or vertebrae are the delay elements. And then you can snap into the idea that we will combine the delays along the back. And if we need more for the feed forwards or more for the feedbacks, we can adjust that. But the direct form 2 is always thought of as being where it has a common backbone of the delay registers. It's just that here's the feedbacks and here's the feed forwards, whereas the direct form 1 has the delays on both the input and the output. So it uses more resources is what it's going on. So from getting into finite precision later on, just thinking about here we have poles first, zeros second, and in the direct form 1 we have zeros first and poles second. What does that mean in terms of dynamic range and quantization effects? That's to be talked about at the end, but it's just kind of the trade-off that goes on there. The biggest thing is M plus N delay blocks are needed in direct form 1, where the max of N and M is what's needed in direct form 2. And I just have this notation in here, canonic form or direct form 2, that shows up in some literature. And I don't think DSP people are as crazy about that, but Grant, you're taking control systems, as Dr. Tromboli talked about canonical, this or that and the other thing, ever?
I believe so.
They love that word, I think, canonical. It's like everybody wears the same kind of shoe. They're canonical. We all wear the, you know, can you visualize that? They just like that. And in topologies, DSP people like that idea too. Direct form 1, direct form 2. So here would be a real simple problem that could be on an exam or it could be in the homework. You're given this h of z, realize it in direct form 1 or realize it in direct form 2. And here is where that minus sign comes to haunt you. So I will try to draw on this to see what's going on. Here we had a minus 1.25 in the original h of z, but it becomes a plus sign in this topology. So you see how that works? And here we have a plus 0.8. So it becomes a minus 0.8. So you just have to remember to flip those signs. The signs don't change when you go from form 1 to form 2, but they do change from the original and back and forth. I don't think our brains will wig out on that. It's just getting used to that idea. And if you're writing code to do this from scratch, not using L-filter or writing it in C or C++, you would have to do this anyway. So now, the more streamlined approach that the book takes the rest of the way through is signal flow graph representation. And this is just a very convenient, and it's based on the fact that there's a large body of knowledge in signal flow graphs. As a matter of fact, since I know, Grant, you took microwave circuit design, and I developed and taught the course and worked with it, there's signal flow graphs there. Control systems people use signal flow graphs. So DSP people use signal flow graphs if they want to. You don't absolutely have to, but if you're curious about how do we use it elsewhere, controls and DSP, pretty much the same idea. In microwave circuits, you use it for incident and reflected waves in an element. And then the signal flow graphs represent return losses or transmissions and things of that sort going through a multi-port or multi-stage system. I like all of it because it's so convenient the way it works out. In DSP, I don't think about this a whole lot, but it certainly is available. In microwave circuits, I don't think there's another way of doing it, actually, that makes sense. So here's a general signal flow graph, and it just shows what's the property of a signal flow graph. A linear signal flow graph is it's composed of directed branches. So I think I say that somewhere in here. Yeah. Directed branches. So unlike what you would think of being in a physical system where you connect a wire from one component to another, you think the signal only flows from one node to the other. It doesn't, because current flows and there's a voltage that's in common, but it's not the same as it is in an electric circuit. It's a directed branch. So signal flows, it does not flow back. And in microwaves, On a transmission line, there is a wave that travels in the opposite direction, but wave theory takes care of modeling that as incident or reflected. So it's still a directed branch for that application, but in software coding, it definitely is true, right? If we copy a sample into the next variable down the line in code, it does not leak back to the input or something like that. So when you're looking at this flow graph where these two branches come together in this sync node, this signal coming along this branch does not somehow or another travel back down over to here, because signals only travel in the direction of the arrows that are in the midpoint of each branch. So this has got a feedback operation in here where it can circulate around, but it doesn't have, it still obeys the rules of directed branches. So we can take the z to the minus 1 out of the block diagram and just write it as a branch that has a z to the minus 1 in it. And then we have source and sync nodes. So the property of a source node is when directed branches are leaving a node, they're just equal copies leaving this node. When it's a sync node where branches come in, you visualize that as being a summation. Signals are combining together. So first order system, go from block diagram to signal flow graph, just does this operation here, where you're just replacing everything with the directed branches, and the summation is automatically defined when the nodes come together. So if you want to write what's present on this branch, it has to be this plus this. If you want to write what's on this branch versus what's on this branch, you don't have to do anything, because something comes in here and it's just a copy of it goes this way and a copy of it goes down there. It's not like in electronics where you'd have loading with elements and things of that sort. I don't know if you enjoy that or not, but that's circuit theory, right? That's what circuit theory is all about. And microwave circuits, same idea. You have mismatches and things if you don't manage things. But directed flow graph, pretty easy. So typically what I will do is I will, if I'm going to solve one, I will write node variables at the nodes where I think I'm going to have to write some equations. I don't have to write them at every one, but here I was really pedantic and just wrote a node variable at every node in the system. And if you have that for this simple system, you can go ahead and write what every node variable is, 1, 2, 3, 4, and then to the output. And you can write all this stuff down. And then if you have to, sort of in a blindfolded way, say that how can I get y of n from x of n, you have to do operations on these equations, maybe not all of them, but some of them, in order to calculate y of n from x of n. So I go through an example here of how I might choose those equations and then write that out. And then you end up perplexed at one point or another. You're sitting right here, and you want to have this connected back over to here, and what's the relationship? But you are sitting in here where you have a problem eventually, where you have this going on. So you have a w of n minus 1, and now when you plug that in into this form right here, you don't really know what to do next, because you need w of n and w of n minus 1. So how can we resolve that? We switch to the z domain. So when you switch to the z domain, this, by virtue of the delay operator, just says that there's a z to the minus 1 there. So that's, try to change the color here. In the z domain, this just becomes this, let's say, a z to the minus 1, something like that. So that's not exactly right as I'm looking at it, but it's the same idea, though. We know there's a z to the minus 1 that comes out of there. So you can start you can get to the end goal pretty readily once you go to the Z domain, because you can use algebra without having the recurrence idea of the difference equation blowing your mind away, trying to do the recurrence part. So you write this out and you get the first order difference equation. So this is where it gets painful, and this type of thing shows up on the final exam where I say, there's a flow graph, tell me what is y of z over x of z. What is the transfer function represented by this flow graph? And you look at this flow graph and you say, that doesn't look like direct form 1, doesn't look like direct form 2, but also understand that flow graph drawing can be like taking something that looked regular and kind of, scrambling it up. And this is not unlike what you might have to do when you have to look at somebody else's code. You know that signal flows in and it comes out. What are they doing here in the middle? You have to sit there and look line by line, like try to straighten the wires out in a sense so that you can get a flow graph that you can understand. What were they implementing here? And that's just part of the challenge in that. If the person documented their work, they would tell you what they were doing, and then how they implemented it in code might be slightly different, but it does the same thing. So this thing is interesting, and when you write it out, you get these equations. When you switch to the Z domain, you get these equations, and then take kind of long-winded step-by-step where I'm trying to eliminate the interior node variables, and this is what you remember from circuit theory. True or false? Remember having nodal equations? I preferred nodes versus mesh. What were your preferences?
I like mesh better.
Okay. We're all unique, right? I like nodes better. But depends on what you're solving, too. So at any rate, I just kind of slogged my way through, and what's unique about this is that it's how my brain was thinking. You will look at it and you will look at it differently. When I grade a problem on this, I end up pulling my hair out because I have to say, you're doing this and this, does that really work, and were you thinking correctly? And one of two things usually happen on an exam in particular. You get so balled up that you lose track, your paper gets messier and messier, and pretty soon I have not the right answer, and I don't know what went wrong because I see lots of scribbling on the paper. The other thing is you're very methodical, clean, and you try to avoid going, quickly to the end because you can't get there. So I just took an approach, and I'm not going to try to step through it. You can look at it, though, and I finally did the simplification and substitutions and worked it all down, and finally get down to this. So if I write y of z over x of z, I've got this, and what do you remember this being? This looks like a type of filter we talked about in Chapter 5. Do you remember? All pass? Remember the all pass? So why would somebody want to do this? Well, if they were going to implement this as a direct form structure, you'd have a coefficient in the feed forward and a coefficient in the feed back. And if those are not quantized in the same fashion, you wouldn't necessarily have the pole and the zero at conjugate reciprocal. So what this topology has done is it's been very efficient. The diagram looks complicated, but that coefficient that's needed in both the numerator and denominator shows up only once. So somebody dreamt this up, somebody that was smart enough to figure out how they could take a first order all pass and make it only require one coefficient multiply. I don't want that to be my claim to fame in signal processing, but there are people have done these things. They've studied stuff like this. So at any rate, that's kind of cool. This is what the direct form would look like. That's in contrast to the way this special form looks. It's just different. It has two multiplies in it, and it has a sign, a minus alpha and an alpha, and depending upon the type of quantization you're using, positive and negative might not turn out the same. But usually they would turn out the same in 2's complement. So now we're going to generalize, and then we're going to try to head to the finish line for this chapter. What do you want to do for IIR systems is you want to consider computational complexity, number of multiplies, number of storage registers. This is the old school way of doing things where we just said these are the 2 driving factors in running fast. But VLSI comes along, and then I didn't make these up. These were taken from a reference. Chip area, modularity, and data transfer simplicity showed up in this list. Does this still apply today? I don't know. I'm not a VLSI designer, but that could be an issue. And then if it's a multiprocessor implementation, algorithm partitioning, and then communicating between multiple processors. And FPGA fits in there too. Xilinx has a lot of, IP associated with buying their products. If you buy their products, you get access to their IP libraries that you can use for different types of filter topologies, a direct form 1, direct form 2, a cascade. And most people say at the companies around town they will use those catalog libraries. Makes sense. They have to start somewhere, so they start with something that Xilinx provides or AMD Xilinx provides. We also have to consider the finite precision effects, so coefficient quantization and then product quantization. And I think a truism that I found when I was reading this article was the network with the minimum number of multipliers and delay elements may not be the least sensitive to the finite precision effects. So you may have to back off from that minimum multiply and add and delay idea to get something that's less sensitive. The only way to find out if you're charting new territory is to test and simulate it. If you're doing old stuff, you just use what's out there and plug into that. So here's a summary of direct form 1, just another picture of it in flow graph form. Summary of direct form 2 in flow graph form. And this is just another example in flow graph form. We already had one earlier. Now a third type of topology, we have direct form 1, direct form 2, we have cascade. This is very popular. The idea with the cascade is you want to have everything into second order sections. So this is the second order sections. This piece right here is just sort of a leftover. If you had an odd numerator and denominator, you might have single first order sections in cascade, but generally you'd still try to group 2 of these together and 2 of these sections together, so it would model this cascade idea that has real poles or complex conjugate pole pairs. But the cascade is, like I said, really popular, and MATLAB and Python and Julia all support that. So this is how you would group things in the first and second order sections if they're real coefficients. I mean, not complex conjugate, but 2 real poles or zeros that are not repeated. So it's called a biquad section that you end up implementing in the cascade, and this is what the biquad sections look like. So NS is the order rounded up to the next highest power of 2, typically. So if you had a 7th order, it would become, you'd round that up to 8, and then the biquad section would be 8 divided by 2, which would be 4. So that's this formula here. And then another question is, what is the ordering of it? Well, that's a question in having to do with the sensitivities, but as the book points out, there's ns factorial squared different pairings. So you can take one second order section, match it here, but then you can take a different one in the numerator and match it with that one, and all the denominator ones can move to match differently. Something that at the very end of the chapter, which I'm not going to really get to, I'll just state the basic idea, is that you want to have a rule of thumb is you want to keep the localized gain in each one of these biquadratic sections from getting too large or getting too small, so that you would have a problem with your precision. So you can pair things up accordingly from the numerator and denominator, and the very end of the chapter talks about that. So here's what a typical biquad looks like. It will have 5 coefficients, 5 multiplies, 4 additions, 2 RAM for data, and 5 ROMs for coefficients, stored as fixed point or floating point, or however you represent them. And then you have difference equations for each of the sections in the biquad. So the way it works, if I'm doing C programming, and I have this in the lab part of the class, so you could look at a lab. I don't remember which lab it is. It's the IIR filter lab, where you do this one, input to output, and then you loop back around and take the output of the first section to produce the output of the second section. Saving state, you have to save the state in this, in this, and this uniquely, because those states are dependent upon where it sits in the cascade. And I have C code that does that. ARM provides filtering code that does that too, for the state maintenance and then the coefficients. But when you do it in C code, not parallel processing, you have to do each section one at a time. If you do it in Xilinx or FPGA, you can parallel process it, because you can instantiate the first biquad, the second one, all the way out to the end using the available DSP slices and other resources on the chip. So that way it's very, very fast. A pipeline fills, and then every time a new sample comes in, a new sample can come out, because it's just one continuous flow with all the biquads firing at once. Whereas in C code, it has to just ripple on down and advance each one at a time, or a vector at a time. In the lab, it's done either as a single sample or as a vector at a time, and ARM has their SimSys DSP library that does that exact thing too. Why people go to biquads, though, over first or type 1 or type 2 is that the sensitivity can be reduced, because each second order section is just looking at the numerator and denominator, which is one pole pair and one zero pair. Whereas when you have a big fat denominator, you have all of these poles that can interact with each other due to the sensitivity created with finite precision arithmetic, and same for the zeros. So people find for large order IIR systems, you have to do cascades, otherwise you have too much sensitivity to the mathematics. Even in double precision math, you can have issues unless you cascade it. This is a simple example in the book of cascading a second order into 2 first order. It's pretty trivial. No one, I don't think, would ever do that. They would just do this as one block, just the second order. But this was an example of what the book did. I don't think I would consider that as a valid homework problem or as a valid exam question. It's like the biquad is the smallest. There's a parallel form which just is based on partial fraction expansion. It's talked about here, but I've not seen it used anywhere. But it is tradition to say that you have direct form 1, 2, cascade, and parallel form. So parallel form might look something like this, where you've got biquadratic sections, and then from long division to make it proper rational, you might have some of those terms at the top from the long division. So that just harkens back to partial fraction expansion. I don't know of any software tools that do this decomposition, though. So there's an example on that from the book. I'm going to step out and go over to another example that was over here. So something that I do in the Jupyter Notebook, and I'm just saving time, trying to save a little bit of time due to where we're at. I did some IIR filter design, and just to show you what my package, which is in Scikit DSP.com, it's called IIR Design Helper. We've used FIR Design Helper a bunch, but this is the same for IIR. So Butterworth, Chebyshev 1 and 2, and elliptic. What I have in my functions, I have it return the direct form coefficients, the B and the A, like we've been seeing a lot of, but then I also have it return second-order sections for this particular filter, Butterworth, Chebby 1, Chebby 2, and elliptic. So second-order sections is provided through, that capability is provided through scipy.signal. I didn't write that, I just incorporated that into my function. So here's an example of what the second-order sections look like for the Chebyshev type 1. You end up with the first biquad is right here. You can see this inner square brackets is breaking it up into 6 coefficients, but in one of the coefficients in the denominator is 1, so that's always true. And so this breaks it up into all the second-order sections that form the cascade. And then I have a function in there that plots poles and zeros directly from second-order sections, and that's Chebyshev type 1, 8 zeros on the back side and 8 poles on the front side where the passband is defined. And this is all of those filter types compared. So we were looking at Chebyshev type 1. This is just comparing different IIR filter techniques. These are the mappings from analog filter design. We don't have time to go through that. I do have a chapter on how the bilinear transformation works and how that theory of filter design works. It used to be a big interest area to me, but now we have tools out there that we just take it for granted. But I do have a chapter on that. It's chapter 8, I think, that has all this detail in it. So if you decide to do a filter simulation and you want to take into account the advantage of the second-order sections, scipy.signal has a function, SOS filter, which will take the SOS structure that gets returned and that let you put X into it. So an example of where this might be important, suppose these coefficients were quantized or it was an extremely tight double precision design filter. In theory, what should happen is this should give you better results than if I was to use the A and the B vectors in just L-filt, because the second order sections would give you that added numerical precision advantage of maintaining the cascade. If it was fixed point, it would most certainly be true. And there's some examples in the notes that go through that later on. But I'm just letting you know that you could do this. Suppose you were building something and all of a sudden the thing, you'd find out that L filter with the A and B vectors is all of a sudden something wonky's happening. You could go to the second order sections idea and see if that would clean it up for a simulation. So, yeah, this last part we looked at earlier already. I'm just kind of trying to hit the right things at the right time. So a couple little trivial little things that are in here about IIR versus FIR systems. We talked about this starting in Chapter 2. The system's infinite impulse response, you hit it with an impulse and it rings or runs for infinitely long, like A to the NU event. So this is an example of the flow graph for that first order system that we saw at the very beginning of the semester. And the nature of the IIR system is its flow graph has a loop in it. So that's what this is. So that's indicating that there's recursion in the system, continually circulating back in a feedback loop. This is one of the big drawbacks of IIR systems, that they have recursion like this, and if there's a chance for some instability to creep in, it would be in a recursive nature, where things could just start going out of control or going unstable. And it might be something in finite precision arithmetic called limit cycles. Very end of this chapter, I'm not going to get a chance to look at that, but it is something that's not really obvious. It's like a tick that goes on in your system, something that the fixed point arithmetic maybe gets going. Now, FIR systems are finite impulse response, and this is like a counterexample to say, just because you see feedback in a loop doesn't mean that it's an IIR system. It could be FIR. In this case, this is the flow graph that has recursion in it. It has that one loop. But if you go ahead and write it out, you see that there's a pole zero cancellation that takes place in here. So you would, if you were quick, you would say there's recursion. This must be IIR. But then if you go through the math over here, you see that cancels. And then you say, why did that person write the topology out needlessly complex? It might just be they got into it on a bad day. They took something they had and they modified it, and then all of a sudden they didn't simplify it. So have I ever done that, things like that, where I build one piece, then add another piece, and it's like I don't go back and clean it up? I think it can be done. Another idea with signal flow graphs that the book mentions is non-computable. And this is, why would anybody do this? Well, you might just do it by accident again. You might have a flow graph that looks like this, and you see there's no delay up here. So you're sitting right here, or you're sitting right here, for example. How do I compute what's right here? Because to compute what's right here, I need to know what's here, and I need to know what's here, but I don't know what's here, because if I trace back, I need to know what's there. So what is that called? Chicken and the egg or something like that, which came first, and how do you do it? So it's pretty easy, though. You just look at this. The difference equation, if you just write it out, is going to be y of n, standing right here, is equal to x of n plus a times that value there is the same as there, y of n. And then you have that difference equation, and you say, oh, I just moved this term to the left, and now it's computable, because I can just write it as a gain scale, 1 over 1 minus a. But you could fall into that trap, and Simulink has a block diagram tool, and it tries to remove in your Simulink block diagram any non-computable loops that are just gain scales like that. So it has a means of doing that. I never really got into Simulink very much, but it had that capability. I also worked with another block diagram tool early on that let you freely wire things together, and anytime you had a feedback loop, you had to automatically assume there was a delay in it. So you could never get into trouble like this, where you would have something that's not computable. I probably spent too much time on that, but it's just something that I was intrigued by early on. I don't really think about it too much anymore, because I don't use that old software that I actually wrote a book on too. I mean, I worked for a company. The company is acquired by Keysight. It's a Keysight product now, but before it was called System View, and they asked me to write an example book using their software, and I wrote it, and it was published. And I never really think about that book, but it used software that had that property. You could wire things up, and you had to pay attention with your feedback loops. This is an interesting topic, though. This kind of one of the final things we're going to look at, transposed signal flow graph. The idea of transposition, and it's a fundamental linear signal flow graph theory, is that it's called transposition or flow graph reversal. Doesn't alter the signal function. So what you can do with SFG is X of n can become Y of n, and a Y of n can become X of n. So you're just going to drive it backwards. And there's a proof based on state variable theory. I used to teach out of this book by Jackson for undergraduates only, and it was a neat state variable matrix theory kind of a proof. But here's what signal flow graph transposition does. It just says if we have a first order system like this, we just let X become Y and Y become X, and then we have to reverse the direction of all the arrows everywhere in the signal flow graph. So these two are flipped, so on, all the way through. And since people might watch this, not understand what I just said, since I did that on the screen there. So it's flipped over. Now, what you would do if you were drawing this out, because our English is, we work from left to right, right? This we don't like. True?
Isn't it the same thing flipped over now?
Yeah, you can just take this, like peel it off the paper and stick it back down again. It is exactly the same thing. And the only thing that's changed in this process is the delay and the coefficient multiplied, their order changed in the signal flow graph. So this is a transposed direct form 2 structure. So it now has the feed forwards up front, and it has the feedbacks in the back, and the backbone of delay, rather than coming down, is now moving up. Both SciPy's L filter and MATLAB's filter function both implement the difference equation as a transposed direct form 2. That's a piece of trivia is what it is. It's just telling me how they wrote their algorithms and how they do the math for it. They use it as a transposed direct form 2. Okay, we're heading in for landing now. So now just simplify a little bit for the FIR structure. The FIR just has feed forward, so you really only have this topology. So you have the standard direct form topology is neither type 1 nor type, it's just the only structure that's available for direct form because there's no feedback, or I mean FIR. So the coefficients, the delay line is across the top, that's one sample delay, and then you tap off the coefficients and then you sum all the way along the bottom. And the other opposite of this is the transposed direct form 2, which just runs in the opposite direction. Because FIRs can be implemented, FIR coefficients are frequently designed for linear phase. That means they're either even or odd symmetric. So if you go to that type of idea, then you can fold the filter down the middle and make this idea here where you're going to run over half as many coefficients and then either have a plus or a minus sign depending upon whether it's even symmetric or odd symmetric. And then that suggests this signal flow graph where you would fold it over so the filter is running around all the way around like this, and you're just going to fold it down the middle. So there's either a coefficient here or there's just a wire there depending upon whether it has a center tap or it doesn't have a center value in the FIR filter. Then you bring them together. This was, I have to tell a little story on this, right? I've been around two stories. I was working for Ford Microelectronics, teaching a real-time DSP class. Ford Microelectronics used to be, let's see, it's a company that's up there. It's near, what's the name of that highway? It's on Highway 83, but it's well before you get to Interquest. It's on the left side as you're driving up Highway 83. I'm trying to think, what is the company that's there? Philips. Philips took over the building that used to be Ford Microelectronics. They were here for a long time, and then they moved back to Michigan. but they did ASICs and other things for RF and digital for automotive applications. And I taught a class up there once. And they asked me some questions when it was all over with, they apparently, at that time, they were using a really high-order FIR filter to smooth the accelerometer data that fires the airbag in a car. Very exciting proposition, right? They don't go off very often. I experienced it in a bad accident a block from my house where the airbags did deploy. It's a very unpleasant experience if you haven't experienced it, but you'll survive it. If things fly around your car, it smells like a shotgun went off. There's gunpowder smell. It's not real fun. It's kind of harsh, but at any rate, they wanted to know if they could take this symmetric FIR filter and make it more efficient in terms of multiplies, and that's where this was the only idea I could offer them, because here you sum things together right here, and then you multiply by the coefficient. So you can roughly cut the number of multiplies in half. So that brought on the question in me, which maybe you would come up with too. How many cars are destroyed in testing an airbag accelerometer system for deploying? You know, they don't like wasting cars at their test facility, but they do have to do it though. Does that make sense? You have to wreck a car, hit it hard enough from a different, whatever the angles are. I was intrigued by it because engineers are more than just electrical, right? We think about mechanics and other things. So.
Well, last summer when I went to Ohio, I went at the museum they had.
In Dearborn or something?
The Air Force National Museum there. They gave us a demo. They showed us around and showed someone who actually experimented with seat belts and stuff.
Mm-hmm.
He was crashing himself into like tons of stuff, and later on got the president to sign the seatbelt law. Wow. That was pretty cool to see.
So is how it changed over time and eventually became a requirement?
Yeah, because they were asking for data, so the only way you could present data was crashing himself all the time. So that's what he did.
I wouldn't like it. I got an injury from the seatbelt. The seatbelt tightened really hard, and I had a rib bruising, and then taking a deep breath was painful because it had crushed my rib cage a little bit. And my wife took an ambulance ride because she wasn't sure if she was hurt somewhere, but she eventually left the hospital. Somebody ran a four-way stop, and I didn't notice that they were coming in, and they were on their cell phone, I'm pretty sure. I didn't have a needs to know, but it had to go to arbitration with the insurance companies, and I eventually won my case. Because a neighbor had their video camera on that intersection, and I got the footage from that, and it just shows me stopping and the other car never stopping. You don't want to do that, though. You can die that way. My wife could have died pretty easily, actually. I don't even like thinking about it. I was afraid to go through that intersection. Okay, so I have a couple of examples in here. The one that are in the notebook, I talk about what I used to use, MATLAB's filter design tool, which is still a very good tool. It's probably the premier product that they have in their signal processing toolbox. It's expensive stuff, but it does everything, and people like using it. I'm pretty content with what Python can offer me, though. You get the coefficient files, and I have ways of handling that in Python, and I also have ways of converting the coefficient files to header files in C, which are useful in the real-time DSP lab. And it does, MATLAB does SOS, does cool things like that. The last thing in here is finite precision. We're really pretty well out of time, but I've been hinting at it along the way, so I can just say issues that get brought up when you're doing finite precision is number representations, coefficient quantization, which you study in a homework problem, quantization noise, which comes about when you're reducing the number of bits after you do a multiply, and then what do you do to deal with scaling? And the basic rule and this I have to deal with on my current project, is I implemented in Python using double precision. I'm ready to put in fixed point as needed, but the guy that I'm working with is implementing it in FPGA fixed point. So we have some issues yet to resolve just to see how it's all going to come together. The last topic, which I already mentioned, was the limit cycle. So we've kind of seen this before, but the most popular way is to think of it as 2's complement. So we have our fractional bits, like if it was 16-bit math, it would be called Q15 because we'd have 15 bits or B bits sitting to the right of the binary point. Then we have our quantizer, and we have the quantization error. This is the same idea used in the A to D modeling. And 2's complement rounding is seemingly the way that most people go with it. That way you have a stair step at 0. And this you go ahead and go through in that homework problem. So I don't think I really need to spend too much time on the coefficient quantization side, but what else goes on in a real system? This is a first order system, so we have just a coefficient A, which will get quantized, but then we have a multiply here, which will have some truncation or rounding error when we do the 16-bit multiply, and then we'll have fixed precision in the continuous to discrete, and maybe a different precision in the discrete to continuous. So you can take that block diagram and you can write a quantize or operation going on at all these different locations. Maybe it's nullified if the bits don't change, but so coefficient quantize, this quantization error is due to the multiplication, and then this would be due to changing the number of bits of precision from a high value to a lower value. So what you can do is at each point there's a quantizer. You can represent an additive noise source, going back to what we did with the A to D modeling. So it's a linear model. And then you have the coefficient quantization. So I think I'm going to run out of time to go beyond the coefficient quantization. I'll just say that the noise modeling you can now do directly by just simulating. I mean, that's what I would do more than likely, but you can model it analytically. Coefficient quantization would first be talked about for IIR systems, and you can do a sensitivity analysis in a numerator-denominator polynomial, and sensitivity just says what is the sensitivity of the 0 location to a given coefficient. And do you remember doing sensitivity analysis in circuits? I'm trying to remember, does that get addressed? Like you tweak a resistor value by its plus or minus 10%, you could find out in the overall network what does that do to the location of a 0 or a pole. I did it when I was in school because I took a course in advanced network theory. It was part of learning about how computer simulation works for networks. So I just remember these partials and things. And it turns out that the sensitivity is the highest when you have 2 zeros that are close to each other, because that gives you a very high sensitivity slope, which is what this partial represents. And you do that for the poles and zeros. So in general, for a system, when you have poles really close together, like is shown in here, then you can have high sensitivity, and that's where the biquadratic sections tends to help out. You only have these 2 poles that are way apart from each other in a complex conjugate situation, and the next section of the cascade has this other pole, so they don't really interact with each other. When they're all over in one big polynomial, then that's where you have your problem. So this is an example that walks through that. This is an interesting flow graph idea, though, that somebody obviously spent part of their life on. Standard topology for direct form, and when you quantize the coefficient, these where the different pole locations can go as you reduce the bits way down, 6 bits, 3 bits. The basic idea, though, is that getting poles that can be located precisely close to the real axes is hard. It's easier the further you go up. Now, that to me is interesting. So somebody came along and they said, let's try this flow graph. And this is a homework problem in the book. This flow graph puts these coefficients in to build the second order section. And this one has a property that as you quantize the coefficients, the locations of the poles are uniformly spread. This seems really cool. Somebody worked this out, though. I find it pretty nice to know. If you use a large number of bits, these problems tend to go, down, and depends upon how fast you need to run and how many bits of precision you need. For the FIR system, which is the one you're going to simulate, you just simply do the sensitivity relative to the coefficients changing. So you can think of it being the desired filter plus another filter that's all the errors in the coefficients. And then that leads to a parallel system model that just says you're going to have some sort of error response in the frequency domain. And that's what you see in that homework problem pretty readily. You can try some other structures to get the quantization better too, but this is what you're doing. Yeah, I'm done. I have to stop because we're out of time.
I cannot get the widget to render through Markdown.
Okay.
To PDF.
Yeah, let me stop the video. Are there any other questions? I'm going to stop the video right now. Got questions coming on the project, but I'm going to take those offline. So